I have finally figured out how to make that record thing work without having to go back to the computer. Finally. 10 weeks later. Okay, so we are dealing with geometric series, and we talked a little bit about how repeating decimals are actually geometric series. We have an algebraic way to calculate what the ratio of these integers would be, or we have a calculus way to do it, and we're going to do it with the calculus method now. So we want to create a geometric series, and remember that the general form of a geometric series, we usually can write a geometric series in that form, usually. And so we're going to try to take these repeating decimals and do that. So when we look at this repeating decimal, the idea is that we're going to want to break it apart. We see that we are dealing with a three-digit sequence that's repeated. And we're going to write out a bunch of fractions and then figure out what the important components of this are. Namely, what's A and what's R. Those are the two pieces that we need for an infinite geometric series, A and R. So let's write this as 37 divided by what? We look at that first grouping of three digits. 1,000. And then we're going to add 37 over another fraction. What will that one be? It will be close to 100,000. I think 1,000,000? I think six zeros? When we have the three digits here, notice that it matches the number of zeros that we put in the denominator. So if we go out 6, we're going to have 6 zeros. And this pattern is going to persist. Let's put some commas in here maybe so we can count those zeros a little more easily. We'll write one more term. And how many zeros are we going to have? 9. So big number, a billion. We should be able to discern what A and R are now. So what is A?
37 over 1,000.
37 divided by 1,000, so 37 thousandths. And then how about R?
1 over 1,000.
1 over 1,000? Right, so R is the common ratio. It's that multiplier that takes us from one fraction to the next. So we're doing repeated division by 1,000, so that multiplier we would write as 1 divided by 1,000. That is our common multiplier. So if we wanted to write it in the standard summation notation, we are starting at 0, going to infinity. The first term is 37 over 1,000. So that's the A. And then R is 1 divided by 1,000, all raised to the k power. And you can double check that this matches. If you plug in k equals 0, you'll get the 37 divided by 1,000, which is our first term. If you plug in 2, you're going to have 37 over 1,000, and then, excuse me, 2. Plug in 1 to get the second term. So plug in 0 to get the first term. You plug in 1 to get the second term, and the second term will have a denominator that's 1,000 times 1,000, which is 1,000,000. And it matches. So that is our series in summation notation. And then we know that for an infinite geometric series, we will have convergence. First note, before I even plug into this formula, we can only plug into that formula if the series converges. And we know that it converges because the common ratio has a magnitude, an absolute value, a magnitude that's less than 1. So we know it converges. Even if it diverged, you could technically plug in the A and the R. Even a divergent geometric series has an A and it has an R. But that value that you get is only meaningful if the series actually converges. So this series converges, so that tells us that the sum of this series is then A, 37 over 1,000. Let's rewrite that so it looks a little bit better. And then 1 minus the common ratio. Easiest thing I think to do here is to multiply through by 1,000. That clears the fractions instantaneously if we multiply everything by 1,000. And we will get the following fraction as our rational number.
Shouldn't that be 199?
Yeah, subtracting 1. Come on, James. Jeez. There we go. So we could have done it that algebra way we learned earlier in the semester. We talked about a couple weeks ago. You could let x equal this thing, multiply both sides by 1,000, and do that algebraic technique. But this is cooler, to do it using calculus. All right, let's try to deal with this one. So we are going to rewrite this one with a pattern also. We've got to be a little careful because the 1 is not part of the pattern. So I'm going to think of this as 1 plus 25 over, what will our denominator be here if we have this repeating pattern of 2 digits? Yeah, 100 will be the denominator. And then we're going to have 25 divided by, when we get out to here, we're going to have 25 over 1,000. 10,000. You said 10,000, right?
Yeah.
And then I said 1,000. And etc. We'll write one more down. So we see that we're adding a pair of zeros each step of the way. So 2 zeros, 4 zeros, 6 zeros. So we're up to 1,000,000 in the denominator, etc. So there is our infinite series. And we know it's a geometric series because there's a constant multiplier. So we're thinking of this as a geometric series plus 1. So that plus 1's not part of the geometric series piece of it. We can think of this as 1 plus geometric series. So for the geometric series part, we're going to focus on that part. A is the first term, so that's 25 divided by 100. And yes, you could simplify each of these fractions. We don't need to do that now, though. And then R is, what's our common multiplier?
1 over 100.
1 over 100. That's going to take us from term to term. And we can simplify the A here. So then our S, well, let's write it in closed form, summation notation first. So we could write this as 1/4 times 1 over 100 to the K. K starts at 0 and goes on forever. So that is our geometric series. That's just this part. We also have the 1. So if I want to make this equal, I'm going to put a 1 on the outside. So 1 plus that geometric series. And if we plug in 0, we're going to get the 1/4, which is 25 over 100. If we plug in 2, we're going to, plug in 1, we're going to get this term. Plug in 2, we're going to get that term. All right. So this, once again, is a geometric series that has a common ratio that's less than 1 in magnitude, so we know it converges. And we know that the sum of a convergent geometric series is A divided by 1 minus R. So for this particular series, we have 1/4 up in the numerator, divided by 1 minus 100. In this case, it might have been easier just to leave the a as 25 over 100, but it doesn't matter. Multiply through by 100. Multiply that by 100, we get 100 over 4, which is 25. And subtract 1 from 100, we get 99. So this will be the series part of it, the infinite series part of it. So this total sum is going to be 1 plus 25 over 99. So our total sum is going to be 124 divided by 99. That'll be our original written as a ratio of integers. So this part is just for the series piece of it. How's that feel? Any questions on it? Errol, question? Everyone see where all the pieces are coming from? I'm just sort of separating it into a constant plus a geometric series. All right. So when you're thinking about a geometric series, the most important property that it has is that repeating multiplication. All right, so that's what makes it geometric. You have this constant multiplier, this common ratio. It's going on and on and on. So as we go through these different series and we start to come up with tests, we need to just keep them all straight. And if you look, I believe we're going to have 10 when all is said and done. So if we come all the way down here, I summarized it somewhere down here. Yeah, so if you look down at the very end, we've got them summarized down there. So we're going to slowly build up all these things. And at this stage, we're going to sort of separate our tests into bona fide tests like the integral test, the ratio test, the root test. And then we're going to have some special series. They're not really tests, but they're series that have special names, like the geometric series. So we're right there. And then the next series that we're going to look at today will be a telescoping. And then at the end of today, we'll look at the P series. So we're sort of in this chunk of space right here. And then we'll get to these bona fide tests. When you have a series that's not a special series, it's just kind of more random, then we're going to go down to these tests. So we just want to sort of keep track of where we are. So right now we're looking at special series. We've got one special series so far, that's the geometric series. Now our second special series is called a telescoping series. And what we are going to see is that the only two series that we will be able to find S sub n for will be geometric and telescoping. If we can find S sub n, we are golden, because then we can just take the limit of S sub n to get S. Most of the time we don't have S sub n. And with the geometric series, we use that idea to come up with the a over 1 minus r. We had a formula for S sub n, we did a little manipulation, and we got S is equal to a over 1 minus r. So the only two series that we are going to be able to find the actual S for, telescoping and geometric. All the other ones we'll be able to tell, do they converge or diverge, but we won't be able to tell what they converge to. And so in general, that's the situation. When you get into other classes that use infinite series, if it's not geometric or telescoping, you have to come up with different techniques. So if you take a numerical analysis class, you'll figure out techniques to figure out how close your approximation is. Like, do you have to go out, if you think about a calculator, and let's suppose your calculator's got 10 digits. When you type into the calculator something like find the sine of 10 degrees, it has to be accurate in your calculator to 10 digits at least so that you can do manipulations with it. And so when you look at the 10-digit display, it's correct. Your calculator uses an infinite series. That's how your calculator does all this stuff. All right, e squared. It needs an infinite series where it can then calculate e squared. You know, anything that's an irrational number has to be approximated. And so these infinite series, at some point, you have to figure out a way to calculate whether how accurate your approximation is. And so in this class, we're only going to do it a little bit, the idea of the approximation and how accurate it is. But in general, when you're going on into differential equations and numerical analysis, you come up with all these integral formulas that give you an accuracy measurement on the approximation, on your S sub n. But geometric and telescoping, we can actually find S if they converge. So most series, we cannot find a formula for the nth partial sum, unfortunately. So telescoping, what does that mean? Well, telescoping, you'll see why it's called a telescoping in a minute. With the telescoping, we want to figure out a formula for S sub n. S sub n is the sum of the first n terms. When your series starts at 1, that's the easiest because that index is actually counting the terms for you. So we're going to plug in 1 to get the first term. When we plug in 1, we get 1/3 minus 1/4. So that is the first term. I'm going to put it in parentheses just to isolate it as a term, even though we don't technically need the parentheses. And I'll put a little number counter down here just to make sure we're seeing that. That's the first term. The second term in this infinite series, we'll plug in the second index value, which is 2. We get a 4th minus a 5th. So that's the second term. The third term, so term number 2, term number 3. Our third term, we will plug in a 3, so we'll get a 5th minus a 6th. And that's going to continue on forever. But we want to stop at the nth term. This pattern will continue forever, but we want to stop. If we're just finding S sub n, we're going to want to stop at the nth term. So let's go out and let's do one term before the nth term, so the n minus first term and the nth term. And so what we've seen is that this is pretty easy. To find the first term, you plug in k equals 1. To find the second term, you plug in k equals 2. What do you think you plug in to get the n minus first term?
Equals 0.
Not 0. So if we wanted the third term, we took a 3 and put it in there. So if we want, let's go to the nth term, it's a little easier. If we want the nth term, what are we going to put in there for k? N. Right? So when the index and the counter match, you're just plugging in the right, that exact number. So first term you plug in 1, second term you plug in 2, the nth term you plug in n. So the nth term will be 1 over n plus 2 minus 1 over n plus 3. So that's going to be the nth term. And then the n minus first term, we're going to plug in n minus 1 in for the k. So n minus 1 here plus 2 is going to be n plus 1. And then that's supposed to be a subtraction in the middle there. That's subtraction. And then 1 over n plus 2. So if you plug in n minus 1 here, n minus 1 plus 3 is n plus 2. So that's the nth term over there. So if you add all these together, that's S sub n. Add all those together. And it's called telescoping because we have this telescoping effect. This cancels with that. So it's all going to collapse like a telescope. The negative 1/5 is going to cancel with that positive 1/5. This negative 1/6 right here is going to cancel with something that's in the muck right here. It's in these dots in the middle. So what we have to do is figure out what cancels and what doesn't cancel. So the only thing that hasn't canceled on the front is that. So now we have to go to the other end and come backwards, come to the left. So think about it this way. As we're moving from left to right, the second part of this term cancels with the first part of the next. Second part cancels with first part of the next. Second part cancels with first part of the next. Now, if we change our perspective and come from right to left instead of left to right, let's start right here. If we were right here, we're going this way, it's the first part of this term that cancels with the second part of the prior. First part with second part of prior. So when we're going this way, it's the first part that cancels with the second part of prior. So first part with second part of prior. So then this first part will cancel with the second part of its prior, which is in those dots. And so what we see is that there's only two parts of this that are not canceling. So this is the simplest type of telescoping series where we only have the one term at the front and the one term at the end. So that gives us a formula for S sub n. So that tells us that S sub n, here is our formula, 1/3 minus 1 divided by n plus 3. So that is our formula for S sub n. That tells us what the nth partial sum is equal to. Bless you. So to find S is the limit as n goes to infinity of S sub n. And what is the limit of that as n goes to infinity?
1/3.
1/3. So that will be the sum of this series. So the sum will be 1/3. Let's see if I can get a little more space in there. That make sense? All right, so now let's do one that's a little harder. This one starts at k equals 3. S sub n always means the sum of the first n terms, regardless of what the k starts at. So once again, telescoping, you can find S sub n. So the sum of the first n terms, and then we can take the limit of it if it converges. Okay, so the first term, all right, what is a little different here? Let's put a k value here. So the k value, and I'll put a number below it. So k is going to be 3 for the first term. Everyone agree? Because this thing starts at 3. So we're going to come up in here, we plug in a 3, and we get 1/4 minus 1/6. So the k value is 3, that's the first term. Now we go to the second term. So the second term, I'll put a 2 in the number row. That means k is going to be 4. So plugging in k equals 4, we get a 5th minus a 7th. Then we're going to go to the third term, which means plug in k equals 5. Plugging in k equals 5, we're going to get 1 divided by 6 minus 1 divided by 8. And I'm going to go one more term just for good measure here, just to make sure. So now we're going to plug in k equals 6. So we're going to get 1/7. Plugging in 6 plus or minus 1/9. Okay, so this was k equals 6, and that gives us our fourth term. All right. Usually 3 is enough, but we'll just do 4 this time. And now on the tail end of S sub n, let's go 3 terms at the end. Let's just be super comprehensive here. So the term number, this is going to be n minus 2, n minus 1, and n. So we want n total terms. So we want the number of terms to be n. The term prior to that's the n minus first term. The term prior to that's the n minus second term. Okay, so tell me what is the k value for the n minus second term?
K minus 1 or something? Oh, negative, yeah. Negative 1.
Not quite.
1 over n minus 1.
Not quite. What is the pattern here? How do you get to the k value from the term number? Add 2. Add 2. So if we add 2 to this, we get n. If we add 2 to this, we get n plus 1. If we add 2 to this, we get n plus 2. So this is the hardest part, this kind of, this sort of shifting thing. So if the first term is generated from k equals 3, the second term is generated from k equals 4, the third term is generated from k equals 5, our pattern here is that to calculate the k necessary that you're going to plug in, you just add it to the number down here. So if we want the n minus second term, we're going to plug in k equals n. If we want the n minus first term, we're going to add 2 to that and plug in n plus 1. If we want the nth term, we're going to plug in n plus 2. All right, so this is the trickiest part is not the calculus part of this. Okay, so we're plugging in n. So we're going to get 1 over n plus 1 minus 1 over n plus 3. So that right there is the n minus second term. The n minus first term, we're going to plug in n plus 1 right here. So we're going to get 1 over n plus 2 minus 1 over n plus 4 when you plug in n plus 1, n plus 4. And then our final term of S sub n, we have to plug in n plus 2. So n plus 2 plus 1 is n plus 3. n plus 2 plus 3 is n plus 5. So there is S sub n. That is S sub n. Let's move that under that. That under that. Everyone tracking? Okay, so now we do the telescoping thing, and we first start on the left, move to the right, and we see that there's a jump. That the second part of the first term is going to cancel with the first part of the term after skipping a term. So second part with first part, but we jump. So second part, jump, first part. And we see when we go to the 1/5, that's not canceling with anything, right? It's only the second parts that are canceling. So this second part is going to cancel with this first part after a jump. And then let's go to negative 1/8. That's the second part. That's going to cancel with the first part of this term over here after we do one jump. So it's somewhere in the muck here. This second term will also cancel with something in the muck. So as we're going left to right, second parts are canceling. So the two pieces that aren't canceling, the two parts, are this first part and this first part. All the second parts canceled. And the first part's after the first two. Now we need to start from the right and go to the left. And I find it easiest if you sort of come to these leading terms and think about going to the left here. What's happening is that your first parts, as you're going to the left, the first part of this cancels with the second part after a jump. The first part of this cancels with the second part of the term after a jump. So going from right to left, it's first parts that are canceling. So this first part right there is going to cancel. That first part cancels with second part after a jump. So we're going this way. This first part is going to cancel with a second part after a jump, so it's going to be somewhere in there. This first part will cancel with something that's in there after a jump. So going this way, all these first parts are canceling, and these two second parts down here are not going to cancel. So those are preserved. you'll always have this pattern that if there's 2 preserved in the front, there's going to be 2 preserved in the tail. So that pattern will always be there. So you know that if you've got 2 here that don't cancel out, there's going to be 2 down there that don't cancel out. So this allows us then to write S sub n in a closed form. It's going to be 1/4 plus 1/5 minus 1 over n plus 4 minus 1 over n plus 5. So that is S sub n. That is the formula for the nth partial sum. And when you have a formula for S sub n, all things are good because you can just take the limit of that. So S will be the limit of S sub n as n goes off to infinity. And what is that limit?
9/20.
So it's going to be that 4th plus a 5th. We'll get a common denominator, so we'll get 9/20. Multiply this one by 5 over 5. Multiply this one by 4 over 4. So we're going to get 5 plus 4 over the common denominator of 20. So that will be our series sum. So these telescoping, we need 2 pieces. You need to find S sub n, and then you find S from S sub n. All right, any part of that that you have a question on? Yeah.
Is it for the telescoping, is there ever a time where it'll be the canceling terms somewhere in the middle, not in the tail at the beginning? Or is it
It's always going to be right at the front and right at the end. Yeah. So the middle, everything's going to cancel, and the preserved terms will always be right near the front and right near the back. And this is about the worst case scenario that we'll see, where the cancellation has this skip in it. You can imagine, you can kind of see a pattern here. Like we have this fractional representation, and you can see the 1 and the 3 differ by 2, whereas up here they only differed by 1. So if they differed by 3, you'd end up with 3 terms in the front and 3 in the back. And so the farther those are apart, the harder it is to figure out what the pattern is. And the more terms you would have to write out to see it clearly.
That's what I was going to say, is like the number of n minus terms is just equal to how many the first terms take to show the pattern?
That's right.
Okay.
Exactly. And so it gets a little, the farther these are apart, the worse it is.
Yeah.
And we won't do any that are more than 2 apart. All right, so this top one doesn't look like a telescoping series. It's not in that sort of fraction minus fraction form, which is the classic telescoping series where you see a fraction minus a fraction. But we have a log property that we all know well by now. And that log property is that if you have the log of a fraction, you can turn that into a subtraction. So this is natural log of k plus 1 minus natural log of k. All right, so that is how we can turn it into a difference. Any telescoping series has to have a difference. That's how those terms are going to cancel out, that domino effect. All right, so let's see if we can do the same thing here. So we want S sub n. So S sub n is always the sum of the first n terms. So here, to get the first term, the k value is 2. So our first term, we're plugging in a 2 for k. So we're going to have natural log of 3 minus natural log of 2. That'll be the first term. We'll put our counter down here. So this is term number 1. And the k value that generated that was a 2. Yeah, more than anything with these, you're just trying to keep track of what's happening. So now we're going to the second term, which means the k value will be 3. So we're plugging in a k value of 3 here. So we're going to have natural log of 4 minus natural log of 3. So now to get to the third term, so term number is 3, k value will be 4. So we're plugging in k equals 4 up here, so we get natural log of 5 minus natural log of 4. Natural log of 4. Now we want n terms. So if we look at our counter row, this is counting the terms, let's just put 2 terms at the end. We'll have our last term, nth term, n minus first term. Now we have to figure out, well, what is the associated k value that will generate that term? So if we look, to get the k value, what are we doing from the term number? So if we add 1 to the term number, that'll be the associated k value. So down here, if we add 1 to that, we're going to get n. If we add 1 to this, we're going to get n plus 1. All right, so let's plug in the k value then of n first. So this will be natural log, plugging in an n right there, natural log of n plus 1. Minus natural log of n. Natural log of n. So that is our n minus first term. And our nth term, we're going to plug in a k value of n plus 1. So it's going to be n plus 2. Plugging in n plus 1 there, we're going to have natural log of n plus 1. So now we have our S of n. And if we look at our cancellation pattern, first part, first part was second part of the subsequent term. First part was second part of subsequent. First part was second part of subsequent, which is somewhere in the muck. So going from left to right, we only have one part of one term that's not canceling out, and that's that one part right there. So first parts are canceling when we go this way. When we go this way, if we look here, from here to here, it's the second part that cancels with first part of prior. And then we come here, second part cancels with first part of prior. So second part cancels with first part of prior. Second part cancels with first part of prior. And that pattern that we've seen already persists. If we had one part in the front that lived on, then we have one part in the end that lives on. So our S of n can then be written as the only part in the front that's persisting, plus the only part in the tail end that's persisting. So that gives us a formula for the nth partial sum. That is our formula. Any questions on generating that formula? So what is S? It's infinite. Right? The limit of this natural log function, natural log, goes up towards infinity. So the limit of this is infinite. This is a constant, a small constant. Subtracting off that's not going to offset this part that's going to infinity. So we end up with a series that diverges. So S is infinite. So our series diverges. All right, you all try this one. So we've got a telescoping series. This one starts at 4. We see the difference between the inners there is 2. So it might be helpful to go 4 terms in the front and 3 terms in the back to see the pattern. So the biggest challenge here is keeping track of your turn number and keeping track of the associated k value. So I recommend putting these little rows beneath it just to keep track. Any questions on computing the leading terms there? So this one starts with a k value of 4. That gives us our first term. K equals 5 gives us our second term, etc. So now sort of the hard part. Down here, we're going to want the n minus second term, the n minus first term, and the nth term. What will be the k value for the n minus second term? N plus 1. So we add 3 to the term number to get the associated k value. So if we add 3 here, we're going to get n plus 1. We add 3 here, we get n plus 2. We add 3 here, we get n plus 3. That makes sense to everyone? So if you think about your k's here, if you subtracted 3, you get 1. If you subtract 3 there, you get n. So that's going to be your n terms. So I just need to plug this in then. So the k gets plugged in. So k is n plus 1. So it's going to be n plus 1 plus 2. So that's n plus 3 inside of the square root minus the square root of n plus 1. This term, we're going to plug in k equals n plus 2. So we get n plus 4 and n plus 2. This nth term, we're plugging in n plus 3, so we're going to have n plus 5 in the square root and n plus 3 in the square root. All right, so now we have our representation of S sub n. We just have to figure out the cancellation pattern. So we're looking at the front here, and first part cancels with second part after a skip. First part cancels with second part after a skip. So we see that going forward, going this way, all these first parts are going to cancel with something that's further on down the road. These two will be somewhere in the muck there, somewhere in the middle. And we've seen that this term this part persists and this part persists. Those two second parts persist. So going left to right, first parts are canceling. Going right to left, second parts are canceling. So second part cancels with first part after a skip. Second part will cancel with first part after a skip. Second part will cancel with first part after a skip. And we have two persisting parts in the back. And once again, the insides here differ by 2, so that gives us a gauge on how many parts are going to be sticking around. So we now have a closed form, or a formula, for S of n. So there is our formula for S of n. We can write the square root of 4 as 2, of course. So that is our S of n. And what is S?
Infinite.
Infinite. So we look at that S of n formula as n goes to infinity, square root of 4 plus n is going to go to infinity. Similarly, the square root of n plus 5 is going to go to infinity. So these two parts are going to infinity, so that's infinite. And you're subtracting off a tiny amount, which is negligible, so this goes to infinity. So therefore, this series also diverges. And we could just simplify the only thing we can do is to simplify this leading term right here. And our partial sum formula could make that a 2. So there's our simplified S sub n, and this series will diverge. All right, so we've got telescoping series now. We call that a special series. So the only two special series we have so far, geometric and telescoping. All right. So some properties when we have a convergent series. These properties should be very intuitive. They should remind you of limit properties. They should remind you of derivative properties. They should remind you of integral properties. If we have a convergent series and we multiply all the terms by a constant, you could just factor the constant out to the front. And the sum of this modified series will be the sum of the original series times that common multiplier of C. That should even look familiar from a geometric series, where that A could factor out to the front, because the A is in every term. So constant multipliers can factor out just like they do with limits, integrals, derivatives. Now this is for a series that converges. So if we have a series that diverges, then if you multiply all the terms by C, as long as C is not 0, that series must diverge. Whether the C is positive or negative, as long as it's not 0, your series still diverges. If you have a divergent series, there's no constant multiplication that could somehow turn it into a convergent series. All right, so if the series diverges and then you multiply every single term by some number, it still is going to diverge. It might go to negative infinity instead of positive infinity, or vice versa, depending on the sign of that constant. But you can't turn a divergent series into a convergent series by multiplying by a constant. The next one, if you have two series that converge, then the series of the sum is going to converge to a plus b. The series of the difference is going to converge to a minus b. So if you have two series that converge, you're just going to do your regular subtraction or addition as necessary. Right, so you can't take two convergent series and somehow turn it into a divergent series. Two convergings is going to converge. Whether you add or subtract, it's going to converge. So if you have two series where one diverges and one converges, same thing. It's divergence is king. You can't turn a divergent series into converges by adding these together. If you have this series that converges, you're adding negligible stuff to the series that diverges, you're still going to get divergence. There's no way that a converging series can offset a diverging series. This one we've talked a lot about already. If we have a series and you chop off the leading terms, so you just start further on down into the series, both are going to converge or both diverge. So if you chop off the leading finite number of terms, you have not changed convergence or divergence. Can't change it. So convergence is not, that's not the right affected, is it? That's that right. That should be an A. Do we all agree on that?
Yeah.
That should be an A in there. Come on, mouse, where are you? My mouse does not want to cooperate. There it is. That is an A. Okay. So when we're thinking about a series, the leading terms don't affect convergence or divergence. But what they do affect is if you have a convergent series, the leading terms are going to be that sort of contribute the most to the actual sum of the series. Right? Because if our series converges, the terms have to be shrinking in magnitude. Chopping off those leading terms, you still have convergence if your series converges. But it's those leading terms that are going to be the largest in magnitude, so they're going to contribute the most to the sum of the series. So if we have a convergent series and you chop off the leading terms, it still converges, but it's going to converge to a smaller number, or a number with smaller magnitude. All right, so the tail is what dictates convergence or divergence, but the leading terms are more heavily weighted to the actual sum if it converges. So this is not, you're not going to be tested on this. This is just an interesting fact. Prior to calculus, back long ago, the Greeks were obsessed with parabolas. And what they did was take a parabola and break it into a bunch of triangles. So they use this thing called the method of exhaustion, where you're just trying to get closer and closer to the full area beneath the curve. And so they broke parabola apart. So we have just this parabolic region. Create this isosceles triangle here. And then you subdivide and you create these two little triangles called a sub 2. And then you're going to subdivide all four of these intervals. And you're going to create a triangle in there, a triangle in there, a triangle in there, and a triangle in there. And the weird thing is that, and you can calculate this very easily, this part. You can go out a few iterations. The triangle a sub 2 is going to be 1/8 that big isosceles triangle in the middle. And that pattern is going to persist. A sub 3, it turns out, is going to be 1/8 of a sub 2. And that pattern persists. So you get this weird geometric series. So first off, the number of triangles is doubling at each stage. So we started with one big isosceles triangle, and then we had two of those little a sub 2s on the sides. And then when you subdivide each of those subintervals, you end up with 4 triangles that are going to be called a sub 3. And then 8 a sub 4s, etc. And it turns out that this weird pattern exists, that a sub 2 is 1/8 of a sub 1. So a sub 2 can be replaced with a1 over 8. Well, the a3 can be replaced with a2 over 8, which is a1 over 64, and blah, blah, blah. You get the point. You can turn all these a's into multiples of a sub 1. That's a geometric series. That's a geometric series, common ratio of 1/4. So the A1 is a constant multiplier. It just sits in the front. The series is going to be A over 1 minus R. That's going to be the area of that parabolic region. And I just put a simple example here. We know how to do this with integration here. We get an area of 4/3. If we use the method of exhaustion, that inner isosceles triangle has an area of 1, half the base times the height. And then that area is going to be 4/3 times that, which is going to match what we get with integration. So you can use that formula up there for the area, and it's going to match what we would get with calculus. How bored do you have to be like parsing a parabola to try to figure out? And there's probably other geometric shapes that you could use this concept of exhaustion. The key for it to work, though, is that you've got to get some sort of pattern between the subsequent areas so that you can turn it into an infinite series. So just an interesting thing. And another interesting thing, so if you go on in math, you'll see some of these interesting examples more and more. The Koch snowflake is the first fractal that most of us see. And the Koch snowflake is found by taking an equilateral triangle, and then you chop out the middle thirds of each and create more equilateral triangles that are smaller. And then you chop out the middle third of each of those and add more equilateral triangles. So you get this mess all the way down to this snowflake-looking thing. And it turns out that this Koch snowflake, obviously it has finite area, because you can put a little box around it, right? There's no way that this area could ever be infinite, because it's trapped inside of a box. But that perimeter, the perimeter is infinite. You know, so this is that. This stuff was developed not too long ago. I was alive. You might not have been alive, but in the 70s is when all this stuff was developed. You know, so they started looking at coastlines and measuring. And it's like, oh, the coastline's length really depends on how long your measuring stick is. If you zoom in and start measuring by the inch, you're going to get a much longer coastline than if you're measuring by, you know, units of 1 yard or whatever, you know, bigger units. And so it turns out you can actually come up with a dimension that's a partial dimension. So length normally has dimension meters, feet, inches, whatever. You can come up with these partial dimensions between 1 and 2 when you're measuring things that are really jagged and sawtoothed. So at any rate, though, we can show that this perimeter is infinite very easily. So I created this little table here that kind of talks about each iteration, segment length, the length of the perimeter, how many extra triangles, and the area of those triangles. And the bottom line is that we can calculate with a geometric series, and that'll be the area of the Koch snowflake. And the perimeter, if you look at the table and look at it carefully, your common ratio is bigger than 1. So it's a geometric series with common ratio bigger than 1, which means that series diverges. So that's going to give us a perimeter that's infinite. So if you want to dive into that a little deeper, you can. And I can answer questions if you have it on it. But as you go on in math and science courses, you'll see more of these interesting examples.
So would this technically be the same sort of like infinite as in like a repeating decimal where it just gets smaller and smaller and smaller?
Correct. Correct. So when you're looking at that, the area is certainly increasing as you add those tiny little equilateral triangles. The area is getting bigger, but it's getting bigger in a negligible way like you just described. We've got those out there in the tail of the series, you're adding things that are super tiny, which is exactly the opposite of the perimeter. The perimeter, you're adding significant length each step of the way, and that's going to lead to an infinite perimeter, even though the area is finite. All right, well, let's take our break there, and then we'll jump into our first 2 official tests for convergence.
That's exactly the point. When we're thinking about the existence of whole numbers, we stop thinking about them just in terms of these. Oh, it was. I had them. If we can now make a conjecture as to what a perimeter could be,
And love not being able to hear for 2 days after the release.
Okay, first test, which is probably the most important test just in terms of scaffolding all the other tests. So this test is called the divergence test. First and foremost, you cannot tell if a series converges with the divergence test. Okay? So the divergence test gives us a way to conclude divergence for egregiously divergent series. So series that are totally divergent, meaning that they just are so bad, like 1 + 1 + 1 + 1 clearly diverges, that kind of thing. So for these egregiously divergent series, this test is really awesome. So what we know is that the only way a series can converge is if those terms are shrinking to 0. If those terms aren't shrinking to 0, there's no way it converges, right? So not only do those terms have to shrink to 0, they have to shrink to 0 pretty quickly. If they don't go to 0 fast, you can have divergence, like the harmonic series we've already seen. This thing diverges. Even though these terms go to 0, and this series can't be referenced too many times because it's such a good test. It's a good way, it's a good intuition builder. It's like, oh yeah, those terms go to 0, 1 over x, but they don't go to 0 fast enough, so that series diverges. Even though the terms are going to 0, that series diverges. So the divergence test says, so we're going to use the contrapositive. So if A, then B, well, if not B, then not A. That's the contrapositive. So this says, if the terms don't go to 0, the series has to diverge. If the terms don't go to 0, the series must diverge. 1 + 1 + 1 + 1, those terms aren't going to 0, that series diverges. This would be inconclusive with the divergence test because the terms are going to 0. So then you have to go use a different test. So the divergence test is just a quick check. Hey, are the terms going to 0? Yes. Oh, if they're going to 0, then the divergence test is inconclusive. Got to do something else. But if the terms aren't going to 0, boom, you conclude it diverges and you're done. So divergence test is something we should always at least look real quickly. Hey, are the terms going to 0? If they're not, then we have divergence. So that's the divergence test. And again, it cannot be used to show convergence. Divergence test either concludes divergence or it's inconclusive and we have to pick another test. So it's one of those two. Never convergence from the divergence test. So this is the difference between contrapositive and converse. So we have this statement, if P then Q. So if that statement is true, the contrapositive is then not Q must imply not P. So that's contrapositive. Converse just means go backwards, if Q then P. And that is not necessarily true. This forward statement and this contrapositive statement are always equivalent. If you've got A implies B, then not B implies not A. That's always true. Those are equivalent. Sometimes it's easier to prove this. Sometimes it's easier to prove that. So if someone says prove this, prove that something is true, sometimes it's easier to do it in this forward direction. Sometimes it's easier to go in this reverse direction. But this is called, I forget what it is, bidirectional, if and only if. Do you know what that word is?
Biconditional, yeah.
So if you have if A, then B, if B, then A, then it's A, if and only if B. It means if you have B, you also have A. If you have A, you have B. So if it goes both ways, that's the converse. Converse is rarely true also. Something has to be very strong for both this direction and this direction to be true. So if B, then A to be true, that's got to be pretty strong. So this is one of those examples. So here, I live in Paris. We're thinking about Paris with that thing, the tower. So if not Paris, those other Parises. So if I live in Paris, I live in France, right? That's true, correct? If I live in Paris, I live in France if I'm living near that big tower, the Eiffel Tower. So the contrapositive is I don't live in France, therefore I don't live in Paris. That has to be true. So those two are always equivalent. Converse, though, I live in France, therefore I live in Paris, obviously false. Right, so the difference between converse and contrapositive. So contrapositive is equivalent to the original statement. All right, so let's take a look at the divergence test then. And when you're going through these things, sometimes you don't even write the divergence test down, but you should at least think about it. You should at least contemplate whether the limit of a sub k is 0. So when we look at this, let's identify a sub k. So a sub k is the expression k cubed divided by k cubed plus 1. And we want to take this limit as k goes to infinity. And what is that limit?
1.
That limit is 1. 3 ways to do it. L'Hopital's rule 3 times, derivative, derivative, derivative. Divide by the highest power of k, or equal powers, matching coefficients, looking at the quotient of leading coefficients, whatever your technique is. That limit is 1. This is not equal to 0. Therefore, this series diverges. Because in the end, it's like adding 1 plus 1 plus 1 plus 1 plus 1 in the in the tail of the series. It's like adding 1 to itself forever, which is diverging. If you add 1 to itself forever, you get a ton. It diverges. Okay, how about the second one? So second one, what is the limit as k goes to infinity of this? So k divided by natural log of k. What technique will we use here? What technique? L'Hopital. So we're going to use L'Hopital's rule here. So we are going to take, so this right now is indeterminate form infinity over infinity, so we can use L'Hopital. We can take the derivative of the numerator, the derivative of the denominator. Let's simplify and then reapply the limit. So limit of k is infinity, so that's not equal to 0, therefore diverges. So if the limit of a sub k is not 0, instant conclusion that the series diverges instantly. All right. How about this one? So limit of a sub k here as k goes to infinity. It's the limit of k squared over 2 to the k. Say again? That's going to be 0. So we have the growth rate chart that we had up on the board last week. And the exponential is going to grow faster than the polynomial, so this limit will be 0. Now, if we wanted to mathematically do this, what technique would we use? We would use L'Hopital. So we take one derivative. Derivative of an exponential is itself times the derivative of the exponent, which is 1. Derivative of k with respect to k is 1, times the natural log of the base. Natural log of the base. So this is still, and because that has power 2, we're going to have to use L'Hopital's twice. We still have infinite over infinite. So now we take we're down to our second derivative. Down here, same thing. Derivative of an exponential is itself times the derivative of the exponent, which is still 1, times the natural log of the base. And so we get natural log of 2 quantity squared. Now we have a limit that is not indeterminate. That limit will be 0. So therefore, this test is inconclusive. So this means pick another test. So if the limit is 0, just like the harmonic series, dig deeper. If the limit is not 0, conclude divergence. Now this one down here, what is this limit going to be?
0.
This is going to be 0, and here we are going to say by growth rates, we don't have a technique to differentiate k factorial. So that k factorial, we don't have a technique at this stage of the game, so that's all we can do, to say that that's going to be 0 by growth rates. So therefore, this is inconclusive. Now let's put on our intuition caps. Do you think this one's going to converge? Do you think these terms are going to go to 0 fast enough? Heck yeah, the factorial function grows really fast. So these are, in fact, going to go to 0 really quickly. We need a test to show that, but intuitively, we expect convergence here because the factorial function grows really, really quickly. Similarly here, we expect convergence. We still need a test to prove it, but an exponential is going to grow notably faster than a polynomial. Even if this polynomial was k to the 10,000, that exponential will eventually take over, and once it takes over significantly. So we would expect both of those to converge, and we'll come up with tests that will show that. All right, harmonic series. So we've talked a lot about this harmonic series. And we talk about it a lot because it's very easy to sort of put it out of your mind and forget that it actually diverges. That you want to have that in the forefront of your mind, that it diverges, even though the terms are going to 0. It's very tempting to think it converges. Okay, so here is S sub n. S sub n is the sum of the first n terms. This counter starts at 1, so that's easy. When the counter starts at 1, that means the nth term is when you plug in k equals n. And when it starts at 1, the nth term is found by plugging in k equals n. So that's the nicest alignment between the term number and the k value. So let's look at a picture. So here's a picture of 1 over x. All right. Looking at these subintervals down here, this is the first subinterval I'm looking at. We're choosing left endpoint approximation, a left endpoint approximation. All right, so these gray boxes are found by looking at the function value at the left endpoints. Does that make sense to everybody from Calc 1, looking at left or right endpoints? So if we look at the rectangle created here, the height of that rectangle is from the left endpoint. The height of this rectangle is from the left endpoint all the way through. So the first rectangle is to the right of 1. The second rectangle is to the right of 2. The nth rectangle is to the right of n. All right. So we've got that approximation there. So do you agree with this statement here that the nth partial sum, the sum of the gray boxes there, and that's S sub n, that's a visual representation of S sub n, do you agree that it's greater than the integral of the function from 1 to n plus 1? Right? We can see it. We can see it right there. S sub n is the sum of these gray boxes. That's bigger, right? There's overhang above the curve. So the area beneath the curve from 1 to n plus 1, that's less than S sub n. It's less than the sum of the gray boxes. Correct? Everyone see that? Okay. So let's just do the math. This is a definite integral. Right, this function is continuous on that interval, so it's definite, it's not improper. So we can do it. So we integrate, we get the natural log. Limits of integration are 1 and n plus 1. Plug in the upper and lower limits. Natural log of 1 is 0, so we get this. And the limit of that as n goes to infinity is infinite. So that tells us that S sub n must diverge. Everyone agree? Right? So S sub n is bigger than this, and this diverges, so then S sub n must diverge. And S sub n is a sequence, and that sequence must diverge because this limit right here is infinite. So if that limit's infinite, S sub n is a divergent sequence, which means the series diverges. The series converges only if S sub n converges. To find the series sum, you take the limit of S sub n. If the limit of S sub n is infinite, well, then the series is infinite, it diverges. So that proves to us that the harmonic diverges. So the harmonic series diverges. All right? So that's our logic there, that S sub n does not converge. So therefore, the series diverges. So that's going to lead us, that concept that we just used with the harmonic series, that concept is leading us to the integral test. So here's our first real bona fide test. The divergence test is important, but it's pretty quick to apply. Limit of a sub k, 0 inconclusive, not 0 diverge. So here we go, integral test. So we've got a continuous, positive, x-axis here, continuous function, positive, decreasing for x greater than or equal to 1. So we've got this, this picture that we've seen a million times this semester. So we've got terms like the harmonic converging down to 0. And so that sequence is embedded within this function. So we've got the regular ski slope looking thing. All right. Well, here's what the theorem says. The theorem says the infinite series and the improper integral, if we go all the way to infinity, so we've got that improper integral all the way to infinity, they do the same thing. If we've got this curve, the area beneath that curve, and then if you look at the sequence that's embedded within that curve, that infinite sum, they're going to do the same thing, which makes perfect sense, right? Because we think about the area beneath the curve as being a collection of rectangles that are added together. An infinite collection of rectangles, which is what we did with improper integration. We had that infinite collection of rectangles that we added up. So now let's get a visual going. So if we look at these intervals here, let me come to the middle one first here. So here's a picture of the integral of f from 1 to infinity, right? When we have our subintervals here, we can choose an approximation from the left endpoint or the right endpoint. I'm choosing this pink one by looking at the right endpoint of each interval. So if I look at the right endpoint of this interval here, that's the height at f of 2, which corresponds to a sub 2, right? Okay, so that's the right endpoint. So down here, I'm going to use left endpoints. So the height of this rectangle would be f of 1, aka a sub 1. So a sub 1 is the height of that one. So we can choose left or right. So down here, I've chosen left endpoints, which is going to create an overestimate for a decreasing function. Up here, I'm choosing right endpoints, which are going to give us an underestimate. But notice that these rectangles are the same from a sub 2 on, right? A sub 2 is that rectangle right there. So this one has no a sub 1 when we choose the right endpoint. But everything else matches. And then out here is a sub n, and out here is a sub n minus 1. So a sub n minus 1, this one right there and this one are identical. So they're just shifted. There's the same number of rectangles in each one of those pictures. It's just that one of them is going to go from 2 to n, and one is going to go from 1 to n minus 1. Same number of rectangles, though. Okay, so the key, though, is to recognize that the pinks are an underestimate and the blues are an overestimate. And so we have this. So the integral from 1 to n of f is trapped in between the blues. We're going to go from, this is a sub 1. We're going to go from 1 to n minus 1, those rectangles. And then the pinks, we're going to go from 2, right, a sub 2 up to a sub n. So 2 to n. and the function's area is trapped in between those two. Everyone agree with that? So we've got one overestimate, one underestimate, and the function's area is, the area beneath the function is right in between. The theorem said both diverge or both converge. They do the same thing. So if we look at this, if this integral converges as n goes to infinity, this infinite series is smaller than converging, so it must also converge. Right? If this integral diverges, so the improper integral diverges, like that thing, well, we have, as n goes to infinity, this represents the improper integral. If this diverges, then our series is bigger than it, so it must also diverge. So if that thing converges, it's bigger than the series, so the series must also converge. If it diverges, the series is bigger than diverging, which means it also diverges. So they're going to do the same thing. If the series converges, well, the integral is less than the series, so the integral must also converge, because less than converging must converge. So we have both directions happen here. So this is one of those bidirectional things. If the series converges, the integral converges. If the series diverges, the integral diverges, and vice versa. If the integral converges, the series converges. If the integral diverges, the series diverges. So they do the same thing. Okay, so let's try to apply the integral test. So we have this function here. First step in our triage process, divergence test. What's the limit of a sub k?
0.
0, right? 1 over a polynomial, a quadratic, that's going to 0. So we're not going to write that down, but we should at least just think and get in the habit of thinking about that. Oh yeah, the a sub k's are going to 0. Carry on. Dig deeper. So the integral test works only if this summand is integrable. There's going to be a whole bunch of series that we end up looking at the summand and you can't integrate it, so the integral test is thrown out the window. So the integral test only works if the inside of the series, the a sub k piece, if it's integrable. So that's the only caveat. And there's all these other things, like we just saw in the integral test. The function is decreasing and positive valued, that stuff. It's going to be true for any series that we look at that's important. The terms are going to be going to 0, so the function you can imagine is decreasing. So the integral test assumptions apply. So let's try to integrate this. So we look at the integral from 1 to infinity. We'll convert it over to x's. So that's the integral that we want to consider. That's an improper integral. So the next thing we write down should be the word limit. And it doesn't matter what letter you choose. This book seems to use B for this process. And the easiest way to integrate this power of x that's in the denominator is to push it up to the numerator and change the sign of the exponent. So now we've got a setup where we can use that power rule. Power rule and RCR and all those things that you've mastered. So to integrate this, we add 1 to the exponent. We divide by the new exponent. But then we also have to do RCR. This is not a 1 right there, so we have to take it into consideration by dividing by the derivative of the base. Reverse chain rule. And this has limits of integration 1 up to b. So now we have a choice. We can factor that negative 1/2 out to the front. Doesn't matter. You can leave it in, pull it out. It's really your choice. But the important thing here is that we have to put the b thing in. And my advice, once again, is get rid of the negative exponents. It's way easier to evaluate a limit when you do not have negative exponents. Negative exponents are an unnecessary distraction. So I factored out the -2 in the denominator. And then we have a b going in here. The -1 power is just a reciprocal. So plug in the b, plug in the 1, do the reciprocal thing. So those fractions are easier to analyze than if you have a negative exponent. Where does this fraction go as b is going to infinity? 0. So that's going to go to 0. Everyone okay with that? Constants, the numerator is constant, denominator is exploding, so the fractions are shrinking. And how about this?
Why isn't that 1 over like 2 plus 4?
Yeah, I was just going to ask that same question. When you plug in a 1, I'm having trouble with ones today. When you plug in a 1, what do we get?
6.
6. So 6 to the -1 is 1/6. Thank you. So then our overall value here is 1 over 12. All right. So let's remember back, improper integration. Would we conclude that this integral converges or diverges? Converges. If we get a number, it converges. If we get infinity, then it diverges. But if we get a number, it converges.
And it doesn't converge to that number, though? Yeah.
So the improper integrals, the true area may or may not be that number. Typically, it's not. Right, so that the value of this integral here, I just misspoke. The value of the integral is 1/12. The sum of the series is not necessarily 1/12. This is the value for the integral. The integral converges to 1/12. But the series does not necessarily converge to 1/12. It could, but it often does not converge to the same thing that the integral converges to. The important thing is that they're linked, that they either both converge or they both diverge. We don't know what the series converge, and this is one of those things that gets a little squirrely, which we talked about earlier. The only two series that we can figure out what the actual value of the convergent series is, telescoping and geometric. Those are the only two. And this is neither of those. Okay, so our conclusion here is that therefore both converge. Now, I want to do something here to make sure. It's so important to understand why something is happening. I am going to put a little extra piece in here. When we get a number, that tells us the integral converges. So I'm going to say this is an element of the positive reals. So this epsilon in this context, this is set notation. This says that 1/12 is an element or 1/12 is in the positive real numbers. So when we're looking at these double barred things, this means the set of all real numbers. And R with a little plus on top means positive real. And we're dealing with a function that's decreasing, so it's got to have non-zero area beneath it. It's a positive valued function. And so this integral is going to converge as long as we get a positive real number. And so I would like that to be inserted just so it's clear, because we are going to end up with lots of numbers, and we have to make conclusions based on those numbers. Sometimes it's going to be this number is bigger than 1, therefore something. Sometimes it'll be this number is less than 1, therefore something. So just here with the integral test, all that's important is that it's a positive real. And if it's a positive real, the integral converges, which means the series converges. So we just want to identify what it is about this number that's telling us what's convergence. And all it has to be is a positive real. And therefore, both are going to converge. All right, let's take a look at this one. First off, divergence test. What's the limit of a sub k? Definitely 0. right? The numerator is constant at 1. The denominator is going bigger, bigger, bigger. So the fractions are going towards 0. All right, so we are going to consider this integral. And I'm going to switch the k's to x's. Okay, so
Does the fact that k is 2 and not 1 impact?
thank you. So this can't start at 1 because what would happen if you plugged in 1 into that natural log function? Yeah, you have division by 0, which is not okay. So this so that one has to start at 0. Start at 2. So we don't get division by 0. Good eye. Yeah, whatever this initial index value is, that will be where your improper integral starts. Yeah, that will always be the truth. Always be the case. What technique of integration are we going to use here? U sub. And we're going to let u equal ln x. And that works great because we see the derivative of ln x right here in front. Right, 1 divided by x is the derivative of ln x. So that tells us that this is going to work. So our next step is going to be limit as b goes to infinity. And we're going to go from 2 to b. And let me write this intermediate step before I actually do the substitution. Just make sure we have our limit set. So then we're going to use u sub. And we're still going to have the limit as b goes to infinity. But we're doing substitution, and we're not going to recompute the limits. We're just going to put some placeholder limits in there. And so let's see. So u is natural log of x, and du is 1 over x dx. So let's just make sure we see all of that stuff is combining to be du. All of that stuff. So it's going to be 1 over u squared du, which I'll write as u to the negative 2 du. Does everybody see where all the pieces are coming from? The du is the stuff in green. So that du is the stuff in green. And then we have natural log of x is being replaced with a u, so that's u to the 2 in the bottom, which means u to the negative 2 in the top. We can use power rule now. So we still have limit. And this is going to be negative 1. Let me write it this way. So it's going to be u to the negative 1 divided by negative 1 with placeholder limits. So we're going to have limit of negative 1 over u. Placeholder limits. And then we'll convert back. U is natural log of x. So negative 1 over natural log of x from 2 to b. You could factor that minus sign out. It's not going to help us a ton in this scenario. So let's just leave it. So we get minus 1 over natural log of b. Minus a minus is plus 1 over natural log of 2. And this limit is as b goes to infinity. Getting rid of the negative exponents helps a lot when you're trying to visualize what a limit is. So how about the limit of that first fraction?
0.
0? Do we agree that denominator, natural log of b as b goes to infinity, that denominator goes to infinity, so that fraction must approach 0. So that's going to go to 0. And limit of this is itself, right? Limit of a constant is itself. So we get that. So our conclusion, this is a positive real number. So it's an element of the set of positive reals. That tells us that the improper integral converges. And then the theorem says they do the same thing. The integral and the sum do the same thing. So our big conclusion is that therefore both converge. So both the series and the improper integral both converge. So if you get a positive real, both are converging. But this number here, that is the sum of the improper integral, but it's not the sum of the series, necessarily. Could be. So that is how the integral test works. So you all tried this one. So try that one right there. What's the conclusion of the divergence test here?
Inconclusive.
Inconclusive. The limit of a sub k, you have a square over a cubic, so that limit's going to be 0. So divergence test would be inconclusive. If the limit is 0, we have to dig deeper. Can you even get a conclusion yet? Did you say divergence? I like that. Divergence. So if we think intuitively about the ratio of the powers here, we have a quadratic over a cubic. If you think in your mind about the plus 5 in the bottom, the plus 5 is very negligible. Adding a constant there is negligible. So if you pulled out the 5, if you just disappeared the 5, k squared over k cubed is going to give us 1 over k, which is the harmonic, which diverges. So our hunch should be that it diverges because you look at the ratio of powers and you end up with a 1 over k. All right, but we have to do the math. Intuition for these infinite series is super important because it can guide us as we're going through. We can see if we're making mistakes more easily. What form is this in? Ish. Log form. The derivative of the bottom is 3x squared, so we'll fairy dust it. Multiply by 1. Sprinkle some constants in there. Now it's in log form. The 1/3 we can factor out to the front. So we have 1/3 limit. Natural log, absolute value of the denominator. We don't need the absolute value bars because everything is positive in this context. We're going from 1 to infinity. So natural log of that. Limits of integration are 1 to b. So we will have 1/3 limit as b goes to infinity, we're going to have natural log of b cubed plus 5 minus natural log, plugging in a 1 gives us natural log of 6. That first expression, natural log b cubed plus 5, as b goes to infinity, that's the inside of a log. A log we know goes to infinity slowly, but it's still going to infinity. So we have infinity minus a constant, which is still infinite. And then we divide by 3, which doesn't change things, so that's infinite. This is not a positive real. Therefore, the integral diverges, which means the series also diverges. So this here we can say, therefore, both diverge. We don't have to put anything else. This is totally fine if both are diverging. All right. Final one of these integral test ones. That thing, divergence test is inconclusive. The denominator is going to infinity, so the fractions are going to 0, but it's inconclusive. So we're going to look at the limit. Oops. First, let's write down the improper integral. So we're going to integrate from 3 to infinity, this horrible looking thing. And then we're going to switch it over. As soon as we recognize that it's improper, we need to introduce the limit. So 3 to b. Okay, so we've got this crazy looking denominator, ln x multiplied by ln of x. What technique are we going to use? U sub? What should we let u equal?
ln of x.
Say that again?
ln of x.
So we could let u be ln of x because we see its derivative, 1 over x is right there. Is that the worst part of the denominator? The other part is worse, right? This ln. Let's just check this for a second. So if we have ln of x, so that ln is inside that one. You don't have to put those parentheses, but that's what it means. I just want to double check that we understand what the derivative is of this. So the derivative of this, first we do the outer ln, so the derivative is going to be 1 over the inside, right? 1 over the inside, multiplied by the derivative of the inside. And what's the derivative of the inside here?
1 over ln of x.
Just 1 over x, the derivative of the inside.
Oh, okay.
So yeah, so you end up getting 1 over x ln x. So the outside function's derivative is 1 over its inside, which is 1 over ln x, multiplied by the derivative of its inside, which is, you got it. So there is the derivative. And isn't that derivative present? So we could do it with ln x, but then what we would have to do is another substitution, a second substitution to get it all the way there. So we can do it in one fell swoop if we pick the worst part of the denominator here. Then we'll get limit as b runs off to infinity. Integral. We're going to put placeholder limits here. We're not going to deal with converting. And so let's highlight the green here. That is all of that. So that part is du. So doesn't this all simplify to 1 over u du? So we said that u is going to be ln x. So that part's u. And then the dx over x ln x is going to be du. So it all simplifies to just 1 over u times du. What's the integral of that? natural log absolute u. And we don't need absolutes here just because everything's positive. We're going to infinity from 3. So this is ln of u with placeholders. Now we're going to convert back. So we're going to have limit of ln of u. U was ln of x. So we have ln of ln of ln of x from 3 to b. So this will be limit of ln of ln of ln of b minus ln of ln of ln of 1. 3, thank you. And this is as b goes to infinity. And where does this first crazy looking thing go to? Infinity. That's going to go to infinity. Infinity minus a skosh, that's a pretty darn small number. That's not going to affect that, so this will be infinite. So therefore, both will diverge. Both are going to diverge. Yeah. That crazy looking ln thing isn't going to make the denominator go to infinity fast enough. Okay, so that's the integral test. The integral test tells us that both the improper integral and the series do the same thing. Now we are going to come to probably the simplest, type of series of all of them. These are going to most closely resemble what we did with improper integration, where with improper integration, our focus was on the denominator. We're looking at the power on x in the denominator, and we said if it was bigger than 1, we had convergence. If it was less than 1, we had divergence. So that is a p-series. A p-series is where we have, when we were doing improper integrations, we had powers of x in the denominator. Here we just have powers of k in the denominator, but it's the same idea. And a p-series is super simple. If p, this is just like improper integration, you would prove the p-series conclusion with improper integration. So if p is bigger than 1, convergence. If p is less than or equal to 1, divergence. And in this context, we're thinking of p as being a positive number. If p is a negative number, what would you have? So if you had something like k to the negative 2,
So it's just a number.
it would be k squared, right? And does the summation of k squared converge or diverge?
Diverge.
Diverge. Okay, so this is true even if you let p's be negative. But typically we're sort of thinking as p being a positive number, either between 0 and 1 or bigger than 1. So that's the idea. You could include negatives if you wanted to. Okay, but that's a p-series. Boils down to exactly what we did with improper integration. So bigger than 1, converge, less than or equal to 1, diverge. If it's equal to 1, don't you just get the harmonic? If it's equal to 1, right? 1 over k to the 1, that's the harmonic, which we already showed diverges with the integral test. But that is a special p-series. The harmonic is a p-series where p is 1. P stands for power. So the power is 1. If the power is 1, you have divergence. All right, this thing. The form of a p-series, you have k raised to the p power in the denominator. So as this stands, we can't see what p is immediately. We have to do some work here. So let's rewrite this. So we want to push that power in the numerator, we want to push that into the denominator. So if we push it into the denominator, we'll do it one step at a time just to make sure it's clear. Right? If you move something to the other part of the fraction, you just toggle the value of the exponent. Change it from positive to negative or vice versa. Now these can be combined using laws of exponents. We can say, oh, well, in the denominator, we have k to the pi minus e. So what I need from you, so I know that you know what you're doing, is you have to identify p. So you would write p is equal to whatever it's equal to. And then you have to compare it to 1. You have to either say that it's greater than 1 or less than or equal to 1. And what is true in this case? Is it greater than 1 or less than or equal to 1? So less than or equal to 1? Does everyone agree? 3.1 and 2.7, yeah, they're about 0.4 apart, so they're less than 1. And so then our conclusion is diverge. For a p-series, bigger than 1 converges, because that means the denominator is growing fast, so the fractions are shrinking fast. And otherwise, this, so therefore diverge. So that's what you need to write. You have to write the letter p down so I know you know it's a p-series, and then identify what p is, and then either say it's greater than 1, so therefore we have convergence, less than or equal to 1, therefore we have divergence. So there we go. Next one. Once again, we've got to do a little manipulation here, and so I'm going to write it this way. And with your indices on a summation, if you just put the 1 there, I know you mean k equals 1 to infinity. You can shortcut it a little bit. Gets old constantly writing all the subscripts. Okay, so the 2 is a constant. It can factor to the front. Like a p-series has this form. There's not a constant in there. So if we have a constant, we want to drag it out to the front and think of it as a p-series multiplied by a constant. And we already know that multiplying by a constant is not going to change convergence or divergence. Right? So we can just look at the series part of this. So now we have to do the identification. You write down p so that I know you know it's a p-series. You identify what p is, and then it's either greater than 1 or less than or equal to 1. Which is it? Greater than 1, and then we make our conclusion. Therefore, it converges. So there's not a lot to write down, but what you write down is important. You know, first you have to rewrite your summation just so that it's in the right form. Identify p, and then make your conclusion. Only 2 choices. Bigger than 1 converge, less than or equal to 1 diverge. All right. So once again, we're not quite, this is p-series-ish. We need to do a little bit more work here. We need to rewrite this so that it's in the form of a p-series. There's no constants other than the power. So we've got to get rid of this 27 thing there. So cubed root of 27, oh, that's just 3, right? And then k, what's the power in k?
2/3.
So that third 3 out there is a third root. So it's in the denominator in the exponent. So that's going to be a 2/3. And I'm going to just put this intermediate step here. You don't have to do this, but I just want to clean it up so that that 3 is not even inside. So now we write down p. It's a p-series. 2/3 is the p-value. Is that greater than 1 or less than or equal to 1? Less than or equal to 1, therefore, diverge. So p-series are very user-friendly. Do a little algebra to rewrite them, pick the p, and then choose converge or diverge based on whether it's bigger than 1 or less than or equal to 1. There's a bunch of these on the worksheet for chapter 10 that will give you some more practice. Okay. So this is hard. We'll do a little bit of this after every few tests. If somebody just says pick a test, that's hard. Because you know, as we get to the point where we have all 10, it can be overwhelming to try to pick a test. So on the exam, I will tell you what test to use so you're not spinning your wheels. At most, I would put one on there where you would have to just pick out of thin air. But we'll practice this as we go. So the first thing, we're going to try to do this in order as we go through the rest of this unit. So we've started with geometric series, telescoping series, and then we had the divergence test, and then the integral test, and then the piece. Wow, we're up to 5. We're halfway there. So when we look at this, you don't necessarily have to go through the order of things that we did. Like, it's not a geometric, it's not a telescoping. Like, that's pretty obvious, right? It's not either of those. Geometric would have a constant multiplier. Telescoping would be separated by a minus. And then we got to the divergence test. So what does the divergence test tell us here? What is the limit of a sub k?
1.
The limit of a sub k is 1. So can we conclude something from the divergence test? Yeah, we can conclude that it diverges, right? Does everybody see that the limit of a sub k is 1 here? So when we take the limit as k goes to infinity, so we're taking the limit of a sub k, that just means the inside. And when you have this square root, if we were being really type A, we would move the limit to the inside. So we have that, because the square root is a continuous function, and that limit symbol can move through continuous functions. It can jump to the inside. And then here, you have your 3 ways. L'Hopital's rule, equal powers, so you get the ratio of leading coefficients, or divide everything by k, whatever technique you want. That limit is 1. The square root of 1 is 1. And our conclusion is what again? So this is not equal to 0. So this is, I want to see that. Why are you concluding divergence? Because this is not 0. So therefore divergence. So we take our limit of a sub k, compare it to 0. If it's not equal to 0, then you know that you have divergence. All right. This one. It's not geometric. There's no constant multiplier thing happening. It's not telescoping. There's no minus in the middle. Divergence test tells us,
Goes to 0.
yeah, the limit of that is 0, so it's inconclusive. And then the only next test we have is integral test in p-series. That looks kind of like a p-series because the only thing happening is in the denominator. You have a power on k, but it's not a p-series because a p-series says 1 over k to the p. So it's p-series-ish, but it's not a p-series. So the only thing we can do at this stage is the integral test. We are going to learn some comparison tests in the near future that would allow us to attack this and compare it to a p-series. But at this stage, all we can do is the integral test. And so we are going to integrate from 0 to infinity that. Improper integral, so we immediately bust out the word limit. And I'll factor out the 10 just to get that out of the way. And so we are going to integrate from 0 to b. And we're going to have dx divided by x squared plus 9. I'll do this improper integration the way we've been doing it. Factor out the 9. Practice some reverse chain rule. Practice some algebra here. So factoring out the 9 is going to put it in arctangent form. So if we factor out that 9, the denominator becomes the sum of squares with a 1, which is a beautiful form when you get that 1 in there. Much less to memorize. That's arctangent. So we have 10 ninths, and then limit and then arctangent of whatever is in the parentheses. And then we have to do the RCR. The derivative of x thirds is 1/3. So we have to divide by 1/3, which means multiply by 3. So that 3 is going to go right in front of the arctangent. And this will be from 0 to b. That 3 constant can factor to the front here and make our leading coefficient 10/3. And then we have limit as b goes to infinity. We'll plug in the b. Now this negative exponent we can't get rid of. This is not a negative exponent in the way that we were talking about earlier. That -1 means inverse tangent. It does not mean 1 over tangent. So we can't get rid of that one. So we have arctan of b over 3 minus arctan of 0 over 3. So that's just arctan of 0. What does this first quantity approach as b goes to infinity?
5/2.
Right, that's an inverse tangent function, so that's our double asymptote. To the right, it approaches pi over 2. And what about arctangent of 0? So arctangent of 0 is 0. The angle on the right side of the unit circle with the tangent value of 0 is 0. Or you can think of the graph going right through the origin. So when all is said and done here, we end up with 5 pi divided by 3. 5 pi over 3. Because this part right here is 0. So pi over 2 times this. So we get that. And what's our conclusion? So this is a positive real. So we're dealing with the integral test. That's a positive real. Therefore, both converge. Yep. All right. Well, we'll stop there. And we'll get to test number 6 and 7 on Thursday. They start to come fast now, so get in there. Get in there, get your note cards going, do a ton, do a lot of math lifting.